right, in this section, let's discuss and dive much more in detail on elementary steps. Elementary steps in a mechanism. To write a rate law for an elementary step in a mechanism, we need to look at the molecularity of that step. The molecularity of an elementary step tells us how many molecules are involved in that elementary step. Unimolecular processes involve only one reactant molecule. Bimolecular processes involve two reactant molecules, and termolecular processes involve three reactant molecules. Unimolecular processes involve only one reactant molecule. So in a unimolecular process, we have an elementary reaction where some single reactant A produces products, and the rate law is just K times concentration of A. For an elementary step, the exponent in the rate law for each reactant equals the coefficient of that reactant in the reaction for that elementary step. Since the sum of the coefficients is equal to the number of molecules reacting in the elementary step, the overall order of the reaction is the number of molecules reacting in that step. So, all unimolecular elementary steps have an overall rate law order of 1. Bimolecular processes involve two reactant molecules, which may be the same or different. So I've shown two different bimolecular processes, one where the elementary step has two of the same molecule, one that has two different molecules, and you can see the corresponding rate laws. The exponent in the rate law for each reactant equals the coefficient of that reactant in the reaction for that elementary step. The rate law is therefore different if the reacting molecules are the same or different, as you can see. The overall order of the reaction is the same, whether the reacting molecules are the same or different. You can see that the sum of the exponents in both cases are 2. All bimolecular elementary steps have an overall rate law order of 2. Termolecular processes involve 3 reactant molecules, which may be the same or different. So I've shown 3 different examples, one where all 3 are the same, where only 2 are the same, and where all 3 are different. The exponent in the rate law for each reactant equals the coefficient of that reactant in the reaction for that elementary step. The rate law is therefore different if the reacting molecules are the same or different, as you can see. It depends on how many different reactants you have, but the overall order of the reaction is the same, whether the reacting molecules are the same or different, because the sum of the exponents is always 3. All termolecular elementary steps have an overall rate law order of 3. Predicting rate laws. Using the tables in the previous slides, rate laws for mechanisms can be predicted. Chemists propose mechanisms for a reaction to understand the pathway a reaction follows. Understanding a reaction's mechanism can help chemists devise ways to speed up a reaction. A mechanism needs to be valid in order to be useful. If a predicted rate law matches the experimentally determined rate law, then the proposed mechanism is considered to be valid. Since a reaction cannot proceed any faster than its slowest step, predicting a rate law from a mechanism starts with the rate determining step. Once the slowest step is used to write a rate law, if the rate law does not contain any intermediates, then that is the predicted rate law for the overall reaction. This will always be the case if the rate determining step is the first elementary step in the mechanism. It's a little more complicated if the rate determining step occurs after the first elementary step, because there will likely be intermediates as reactants. In that case, the other steps in the mechanism will need to be used to replace the intermediate with an expression that contains only reactants from the overall reaction. The intermediates cannot appear in a rate law for the overall reaction. Example 1, slow initial step. So here's the overall reaction. NO2 gas plus CO produces NO gas plus CO2. The rate law for this reaction is found experimentally to be rate is equal to K times concentration of NO2 squared. CO is necessary for this reaction to occur, but the rate of the reaction does not depend on its concentration. The rate of the reaction only depends on NO2. This suggests the reaction has more than one step. A chemist might hypothesize this mechanism for the reaction, where step 1, NO2 plus NO2 produces NO3 plus NO as the slow step, and NO3 plus CO produces NO2 plus CO2 as the second and fast step. The NO3 intermediate is created in the first step and consumed in the second step, so that our overall reaction looks like the one we saw on the prior slide. Part A, what is the molecularity and rate law for step 1? So step 1 has reactant A plus reactant A, but 2 molecules of it. So this is bimolecular, right? Bimolecular. And the rate law would equal K NO2 squared. B, what is the molecularity and rate law for step 2? So we have 2 different reactants here, A and B, but still bimolecular. So the rate BK NO3 CO, which is consistent with experimental data. So on the previous slide, we said that the experimental data showed this to be the rate law. So step 1 is consistent with experimental data. All right, so here we see the 2 rate laws and molecularity shown in a little more detail. And again, just to be more clear, which is consistent with experimental data, the rate law for step 1 is consistent with the data. So step 1 is the slow rate determining step. When the rate law for the slow step matches the experimentally determined rate law, the mechanism is considered valid. Example 2, fast initial step. So you have NO2, 2 NO2 gas plus Br2 gas producing 2 NOBr. This is our overall reaction. Experimentally, the rate law is K times NO2 squared times Br squared. Because termolecular processes are rare, and the reason is collision of 3 molecules in the correct orientation is very difficult, this rate law suggests a 2-step mechanism. A proposed mechanism for this reaction is shown. Step 1, NO plus Br2 produces NOBr2. NOBr2 plus NO produces 2 NOBr. Step 1 includes the forward and reverse reactions. The rate of the overall reaction depends upon the rate of the slow step, which we see here is step 2. Remember, the example here is for a fast initial step. So that would mean the second step is the slow step. The rate law for that step would be what we're calling K2 times concentration of NOBr times concentration of NO. But the rate law for a reaction cannot include intermediates. since those only exist briefly and are difficult or impossible to directly measure. We need to make a substitution which will eliminate NOBR2. We can use the first fast elementary step to do that. So here's that first fast intermediate step, or that first step that includes the intermediate. This step can proceed in either direction, forward or reverse. The rate constants for those two directions, K1 and K minus 1, or inverse K, are not necessarily equal, but the rates must be equal. So the two rate laws may be set equal. So the rate of the forward reaction, the one that goes from left to right, is K1 times concentration of NO times concentration of Br2. That has to equal the rate of the reverse reaction, which is K minus 1 times concentration of, if we're going in the reverse, this would be our starting material, so NOBr2. Okay, so I set the forward and reverse rates equal, substitute the two rate laws in, and solve for NOBr2, which I can see right here. This expression for NOBr2 can now be used to eliminate NOBr2 from our rate law that we wrote on the previous slide. So let's take a look at that now. All right, so carried over from the previous slide, here's our rate law for the slow step. I have to substitute for NOBr2 right here, which I've done inside these large parentheses. That's our result from the previous slide. The ratio of the two rate constants, forward over reverse, times concentration of NO times concentration of Br2. And then I can simplify. So I've combined all these rate constants, and I'm replacing the three rate constants, K2, K1 over K minus 1, with one new rate constant, K. And then I have NO times NO, so NO squared, and then the concentration of Br2. When the rate law for the slow step matches the experimentally determined rate law, the mechanism is considered valid. Example 3, predicting the rate law. Predict the rate law for the overall reaction based on this mechanism. Step 1, we see NO2 plus Cl2 produces ClNO2 plus Cl. That's the slow step. And then in the second step, NO2 plus Cl produces ClNO2. That's the fast step. And then we combine to get our overall reaction. Maybe try this on your own, and I will review it on the next slide. All right, so this one is a little more straightforward because the first step is the slow step. So it's the rate determining step. The rate determining step is bimolecular. We have two molecules to start out with. So the rate law is based on that step. From the table for bimolecular elementary steps, the rate law is rate equals K times concentration of NO2 times concentration of Cl2. And if we compare that to our overall reaction, this rate law does not contain any intermediates, so this is the predicted rate law for the overall reaction. Example 4, predicting the rate law. Predict the rate law for the overall reaction based on this mechanism. So we have two steps, the first one fast, the second one slow. So this one's a little bit more complicated because our rate determining step, our slow step, if I write the rate law, it would be K2 times concentration of AB2 times concentration of B2. Here's the problem. AB2 does not appear in our overall reaction. It's an intermediate, right? So I need a rate law that does not include AB2. I need to substitute. So I need to go back to my first elementary step, the fast step, and let's do the rate of the forward reaction. So it's K1 times concentration of A times concentration of B2. The rate of the reverse reaction is K sub minus 1 times concentration of A, B, 2. We can set these equal to one another and see that concentration of AB2 equals K1, concentration of A, concentration of B2 over K minus 1. Now what we're going to do is take all of this and substitute it in here for AB2. All right, so picking up where we left off on the previous slide, for AB2, we're substituting our results K1 over K minus 1 times concentration of A times concentration of B2. From here, we just need to do some simplification. We have all this ratio of K's here that we just call the overall K for the reaction times concentration A times concentration of B2 squared. And this is our rate law now with no intermediates. Steady state approximation. When reaction mechanisms have several steps, it's not always easy to find the slowest step. If this is the case, it's useful to consider the concentration of an intermediate, which we say concentration INT for intermediate, that has a constant concentration during a reaction, meaning that the intermediate is consumed as quickly as it is generated. So when this is constant, that means the concentration of this intermediate is staying the same. That means it's being made as quickly as it's being used. Okay? For example, if we consider the reaction where A produces B, produces C and D, where B is the intermediate. I've just combined the two steps into one, but I could have A plus B in step 1, or A produces B in step 1, and then B produces C and D in step 2. The formation of B would be expressed as this derivative. Change in the concentration with respect to time would be K times A1 minus K minus 1 times concentration of B minus K2 here, concentration CD. Since we assume the concentration of B is staying constant, we'll set this derivative equal to 0 and then solve for B. So I just set the whole thing. How we get this is not of most concern. But once we set it equal to 0, we can see that the concentration of B is this ratio of K's, again, K1, which is this forward reaction, times concentration of A, this reactant, minus K2, this rate constant, times concentration of C and D, over K minus 1, this reverse rate constant.